Welcome to my YouTube channel. Last time we were examining the Pye high fidelity, says high fidelity there, Mozart HF10, which was made in 1957. It was faulty in the workshop, and we managed to repair it in the last video I showed you all. And I said that I might just do a frequency response of this amplifier, so that's what I've set up to do now. At the present moment, we have some test equipment. You can see here is an AC voltmeter. It's rather an old one. It's a Marconi TF2600. But as you can see, I've set it up so that the input oscillator is being measured there at the input across these terminals here, and the output of our oscillator, audio oscillator, is on this scale 500 millivolts. We're on the 100 millivolt scale, 100 millivolts there, so that's 50 millivolts, exactly halfway. And we've got the frequency at the present moment set to if I could just show that, 1 kilohertz there. We have an output. The connection of the output is onto an 8-arm rheostat here, just an adjustable rheostat. It's quite a, there's 10 watts coming out of this thing, or there may be. So I've got a rheostat there, and I've got a scope measuring the output. Whoops, I just dropped the camera. I've scoped the output, and there's a 1 kilohertz waveform. So all we have to do to measure the frequency response of this amplifier here is to make sure that the input level is constant at 50 millivolts, and we take various measurements, frequency measurements, okay, and we record the output level on the scope for each frequency that we are going to set this up for there. And if I can show you, I've done a table of output level and frequency for the Pye Mozart HF10 audio amplifier, and I've tabulated frequencies between output levels of frequencies between 20 Hertz and 28 kilohertz. I've recorded the input level here at 50 millivolts constant all the way down through, keeping that absolutely at 500 millivolts there each time I change the frequency here. And as you can see, the output volts are recorded here all the way down there to 28 kilohertz, and you notice that the output volts drops from 3.25 volts all the way down to 1.88 at 28 kilohertz. And what we're going to do is we're going to tabulate these results on some logarithmic graph paper, which I'll show you in a minute. We work out the output dBs using this formula, 20 logs to the base 10 of the voltage out over the voltage in. So we work out V out over V in first, and then we take the logs to the base 10 of that, and then the answer to that we multiply by 20, and that'll give us decibels. So taking this value here, first one at 20 Hertz, we had an output voltage of 3.25, so that becomes V out, and of course the input is 50 millivolts, so we divide 50 millivolts into 3.25 according to the formula. We find the log to the base 10 of that and then multiply by 20, and these are the results for each reading we've done here. Then what we've got to do is we've got to work out what the relative dBs are relative to 1 kilohertz. So we'll call the 1 kilohertz dB level 0, okay, and then we'll work out what each value of this is in terms of its relative value here. So all we'd have to do, for instance, here, as you can see, we've got 36.2, and at 1 kilohertz, we're going to call that 0. So we've got a gain from 33.51 to 36.2 of 2.69. You just simply take that figure, okay, take that figure there, and you take that one away, and so on, all the way through this table, and these are the results you get. And you'll notice that relative to 1 kilohertz, which we'll call 0 dB R, relative to 0 dBs at 1 kilohertz, we have a gain of plus 2.69 dBs at 20 hertz, and it starts to drop down here, and it becomes negative at 2 kilohertz, and we go all the way down, all the way up to 28 kilohertz, and it drops to minus 2.1 dBr relative to 1 kilohertz there. So we're going to tabulate that on some graph paper, and these are the results. This is logarithmic graph paper because we want to get the 10 hertz here, 10 hertz, all the way up to 20 kilohertz there. So you have to have it's quite obvious really, you've got to have a logarithmic scale where this starts to get smaller here, and then it expanded, and then it's getting smaller, and so on, expanded and then getting smaller at each decade of frequency. So there we have it, and that is the result. We've got, if I can focus the camera, we're getting a drop off here, okay, and then it rises from, well, 10 hertz is well below minus 3 dBs, and then it rises up here to 0 at about 700 hertz, okay, and then it's flat. There's no loss or gain all the way through, dead flat, until it reaches this point here, which is 15 kilohertz, and then it drops off. And what I should say, okay, because I have been looking at the graph, is that this is an ideal graph. It's not the actual results of the amplifier itself. I drew this as an ideal frequency response of what it should look like. I forgot to say that. Should have prepared myself a little bit more. But I've actually got the graph somewhere or the other, and I've actually drawn the graph, and so I'm just going to pause the camera while I get the graph. Hello there again. It's always the thing, isn't it? The best laid plans always go wrong. I was showing you the ideal frequency response graph, and this is the plotted one of the actual amplifier here. I've plotted the table of results there onto this graph paper. So I'm probably labouring the point too much, but as you can see here, this amplifier at 20 hertz has a gain of about 2.5 dBs, then rises to just over 3.5 dBs at 700 hertz, and then it starts to fall off at 100 hertz. There it's 3 dBs at 100 hertz plus 3 dBs, and then it drops down here until we get to 1000 hertz, a kilohertz, and then the level is 0 dBs. That's what our relative dBr is. So then, as you can see, the response remains more or less flat, and then it tails off above 10 kilohertz slowly to 20 kilohertz. It's about where are we? About -2 at 20 kilohertz. So between 20 kilohertz, where it's -2, and 20 hertz, which is plus 2, 3. We got 5 dBs. Okay, between our highest frequency and our lowest frequency. So basically, what you've got to remember is that the human ear cannot detect a rise and fall of 3 dBs. If you've got a gain of 3 dBs or a loss of 3 dBs, your ears will not be able to detect that. Okay, so if you look at this graph here, okay, at the lowest frequency, call it 3 dBs, okay, from 20 hertz all the way down to 1 kilohertz there, okay, there's a loss of approximately 3 dBs. You will not be able to hear that, the difference of if you put 20 hertz in there and then you put a kilohertz in there. Although the graph looks as if you will not be able to detect, your ears will not be able to detect that change in level there. And from 1 kilohertz right the way up to 20 kilohertz is much less than 3 dBs. It's about 2 dBs. So you certainly wouldn't be able to hear that drop in level there. Your ears just won't detect it. Or if you've got very, very good ears, you might just about. So you would hear a difference from here around about, what was this frequency here, about, let's focus the camera, that's about 500 hertz, where we got the maximum level of 3.5 dBs. So you would be able to hear a difference in level from there right up to here. You would be able to hear that this amplifier is a little bit louder at the low end than it is up at the high frequency end. But when you're playing music, you're not liable to really detect that difference much. Well, that's a little bit long-winded. I would expect, as I started this video going, I would have expected to see a graph rather like that, where it tails off up above 15 kilohertz and it drops down below 500 or 600 hertz down, but it doesn't. That's sort of, I'll try and focus the camera again. That's a sort of ideal response, and that is the response curve of this amplifier. Quite surprising, actually. It sounds okay, but compared with modern audio, transistor audio amps or solid state amps, that frequency response is a little bit bottom endy, as we would say. it's a gain at the bottom end, and you'd have to be careful that you don't overload this amplifier too much by turning up the volume too much, because at the bottom end you're going to start bringing in some distortion, I would think, if you had the listening levels very, very high. But there we are. Thank you for looking, and just before I close, I would just show you what I actually did as the method. The apparatus is a sensitive AC voltmeter. There, you can have anything you like. I just happen to have an old Marconi one. An oscilloscope, I use a Tektronix. It's that one. It's a sort of cheapy thing, really. Well, they're cheap. I think they're well over £1,000 now. An audio oscillator, that's very cheap. A little, I don't know what make it is. 10, yeah, American company. And then the fourth thing we have is an 8-ohm rheostat, which is there. Any old resistor will do, as long as it's got, say, 10 watts of it's a 10 watts rating. Then the method is simply this: connect the audio oscillator to the amplifier's radio phono input. That's round the back there, just there. Making sure the radio input is selected at the front, there. There, selector, which it is. R, as you can see, radio. Connect the AC voltmeter across the audio oscillator, which we've just done there. There's the oscillator, there's the level. Connect the 8-ohm rheostat to the amplifier's 8-ohm speaker terminal, obviously. Okay. At each frequency from 20 Hz to 28 kHz, record the output volts as measured on the oscilloscope, keeping the audio oscillator input constant at 50 millivolts. That's very important, keep it 50 millivolts. And then point 6, calculate the gain in dBs using the formula 20 log 10 V out over V in for each frequency step. Calculate and tabulate dBr at each frequency. dBr is relative to 0 dBs at 1 kilohertz. And lastly, using logarithmic graph paper, plot the frequency versus dBr from the table of results. There we are. So that's it. And that will take you back to some of you, to your technical high school days or college days, when you were doing your HNC or your BSc or whatever it is, and you did all these experiments and things. This is what you had to do. You had to draw the apparatus, you had to tabulate the results, and you had to write out the method and everything. So that might take some of you back to your school days, or college days, I should say. Anyway, thank you for looking, and I hope you found this helpful.